Boy, you're just celebrating all the time. Just don't know when to stop it.
I'd like to talk about Lynns' approach to all this twisted invariance. And what we did last week, among the things, we talked primarily about how to get what is invariant, mostly combinatorially, and we will talk about other approaches, the particular homological approach to this tomorrow. But I think it's good to go back and look at Lynns' approach, because it gives us a lot of intuition about what to expect in the invariant. So the paper that I'm referring to is representations of knot groups and twisted Alexander polynomials. And this appeared Acta Mathematica, 2001, but in fact, this was a preprint for many years, and I think 1990. And Chasson said that he had so many requests for this that he finally thought he should write it up and make it generally available. So Lynns' approach generalizes the Cypher surface approach for computing the untwisted polynomial, the untwisted Alexander polynomial. And here's the setup. Let S be a Cypher surface for K, and let's choose a basis for the first homology. And I'm going to be a little bit sloppy about what's a oriented simple closed curve and what's a homology class, and we're not going, hopefully we won't get into any trouble. So A132G is a simple closed curves oriented, representing a basis for the homology of the Cypher surface with Z coefficients. So this is a free-wheeling group of 2G. And the VB, this is all very, very standard. So it's always nice to see something we recognize. So only the mistakes will be new, right?
Excuse me. Say the size is Cypher surface closed?
No. Oh, so
why is it
because it's a surface with boundary, and you can retract it onto its. I'll draw a picture in a moment. You can retract it onto a bouquet of circles. So if you think of a punctured torus, a genus 1 surface that has one boundary component. So take a little disk out of an unknotted torus.
Oh, okay, yeah.
You see that
only one boundary.
Yeah, only one. Yes. Yeah, we're assuming it's a Cypher surface for a knot. Okay, so V is a linking matrix, and we'll denote its entries Vij, and Vij is the linking number. Boy, my handwriting is this bad Monday morning. Linking number. I'm going to do it this way. I'm going to. There's variations on this. I'm going to push off the first component in the positive direction. I'll explain what this means, and then take the linking with the j component. So AI plus is a push off of AI in the positive normal direction. And what do I mean by positive normal direction? Well, we can assume that the knot is oriented. And so there's a little piece at the edge of the Cypher surface, and here's the knot K. And let's see, we orient it this way. Then if we imagine the right-hand roll meridian linking this thing would come up. And I'll just choose this as my convention. So this is my positive direction. So we take each representative of each generator for the homology, we push it up, and we see how it links with the J generator that's still lying on the Cypher surface. Okay. And likewise, one can define AI minus to be the negative, push off in the negative direction. And so one can define Uij to be the matrix of linking of this AI minus. And then it happens in this case here, but this happy circumstance won't last. Here that it's easy to check that U is in fact B transpose. Okay. But the classical Alexander polynomial then is well known. It's defined to be. You can define it to be the determinant of T times V minus U, which is the same as the determinant of T times V minus V transpose. Okay. So let's just see briefly why this is so. It's not difficult to see this. All right, I want to draw a knot exterior, and this is actually what you get if you took not S3 but S2, and not S1 but a codimension one thing, which is 2 points, and you remove a neighborhood of 2 points from the two-sphere, and you get an annulus. And so this is the you could say this is a longitude on the torus, which represents the knot K. Just think of it as the knot K. And this would represent what you see with the Cypher surface. So it's actually a very useful picture. So here's the meridian going around. And this is the exterior. And if we cut along S, then we'll open this thing up to a covariance. And we'll see 2 copies of S. Imagine it's cut. So there's a copy S here, and there's a copy S here. We could label them plus or minus, but the important thing to notice is that we have a positive direction, and that positive direction we push it up here. Now, if we stack copies of this, and let's call this Y. Let's call it Y, cut open thing. And now if we goes and stack all the resulting copies that we make, so copy and cut, copy and paste. Then we put these together, and we get the very familiar, at least some familiar picture of the infinite cyclic cover. So here's one copy of Y. And you can think about our deck transformations, which we've been calling a group generated by T. You can think about the deck transformations as pushing these copies along. So you can think about this as T1. And of course, this would be T goes to Y. And so what we have up here is what we're calling X prime. Preserve our notation and our sanity. This is the infinite cyclic cover. Now, if you want to form the first homology of the infinite cyclic cover, you can use Meyer torus with countably many copies. And really, all you have to do is take copies of the homology, direct sum. And I'm just going to write Ty here just to keep track of things. Of course, this is isomorphic to this. These are all isomorphic copies of each. And then we have to just amalgamate certain generators. We have to amalgamate what's going. We have to say what's going on when we glue these things together. And what's going on here is that AI minus is the same as TI AI plus. So I'm using the same generators, AI in here, and calling them AI again in here. So I've got A1 through A2G here, but I've also got A1 through 2G here with T's in front of them. Some building a module structure. And why does this happen this way? Well, because over here, if I take AI and I push it over here to TAI, then that should be glued to AI pushed in this direction, just moved over here. When you think about a collar, you can see why this would work. So AI minus, which is really living in Y, is going to get glued to the translative AI plus. It's over here. It's a rule. That's how it looks. And in fact, we can write down a presentation for the homology as a ZTT inverse homology. And it's just simply A1 and 2G. And we just have to do this everywhere. Of course, we're writing these things as words in A1 through A2G, but you know, they are something else. And there's a very nice way to write these things as words. So what you have, let me say it this way.
I have a rather simple question. Why is the relation not A plus I equals TA minus I, just because of the choice of T and T inverse? Of which way is positive?
Yeah, it's going to be. We have to be careful about this. We can. I mean, you can arrange it either way, but when we go to the group of the knot, and we see the way the conjugation works, then we have to be very careful. If you wish to do it the other way, you can. You just pay a different price later.
Okay.
But I think.
I mean, in your presentation, what particularly do you mean? I mean, in your relations, you have these symbols with plus and minus. Are you taking two sets of symbols?
Where in the presentation? No, I'm thinking.
AI on the left.
I'm thinking about. If you wish, you could think about it this way. You could think about symbols AIJ, where the J corresponds to which copy we're in.
Okay.
But then, if we want to induce a module structure, this is as a ZTT inverse module, then we can simply define this to be taking AI0 to be AI. And we're simply saying that TJ AI is going to be thought of as AIJ. And with that, so this is our AIJ.
Is T
I think it's
But you still have
T is shifting us this way.
and plus?
symbols on the right.
Yeah.
I would guess it's.
Yeah,
I would guess it's T inverse.
You gotta stare at this. It's the trouble is that AI plus is here.
So that element
Equals
AI minus.
But now think about it over here.
But that element you just drew, the little curve you just drew, is T inverse of AI plus in the next piece.
That little piece, this one here.
That curve is T inverse.
Yes. But T inverse is, so I want to just look at this chunk right here.
Yeah.
Okay? And I want to just push in a little bit. Okay?
Okay.
So that's all I'm doing. I'm pushing in a collar. Yeah? But now think about the same picture over here. And think about
TA.
so that same curve is over here. Yes? Okay? But I want to glue it. I can think about this. Now this is in the next piece over here. It's TAI. And I've got to glue it to something over here. Yeah? So what's it going to be glued to? It's going to be glued to the thing that's the other push-off in the other direction in this piece. So in this piece, In this case, it's AI minus.
No,
I
make
think
another
it's
comment
right. It's a little
that
screwy.
maybe it'll straighten this out, I'm not sure, is I would instead of writing A1 through A2, I'd pick generators for the homology of the Y, and then AI minus can be written in terms of that.
Right.
And AI plus can be written in terms. So,
Yeah,
in other words, the A1 in your presentation is not the lift of a curve on the Cypher surface
Sure,
in the
sure.
infinite cyclic cover.
But I'm going to do that in a second.
Okay.
Yeah.
But I mean, I think it. Never mind.
Yeah.
I'll let you go on.
Okay. Well, I think. Yeah. This is. I think I'm going to do something like that in just a moment. But right now I'm gluing things together as one would do it on the fundamental group level. If you wanted to pass the
I'm
presentation.
just objecting to the letter A1 in your presentation,
Right.
because it's really.
But A1's going to be traded away for something that really corresponds to a nice basis for here. I'm going to do that. There's a lot of ways you can do it, and yeah, to some degree I'm also following the Lynns approach, and also, but I can see different points of view. This business about which T is, I think that's okay. I struggled with it a bit. As long as you're consistent, everything's all right. But some funny business here. So look, H1 of Y is has a dual basis. And I'll call them alpha 1 or alpha 2G. And the idea of the dual basis is these are alpha I links AI exactly once, but doesn't link any of the others. So here's a simple picture. Simple picture. Tell you how to define them. This is actually a trefoil, and we take a base point here, and if this is A1, and this is A2. Then alpha 1 is here, and alpha 2 is here. So the idea here is that that the linking of alpha I and J is, I have it going in the right direction? Yeah, is a prime by J. And now in terms of this, which is what Pat's suggesting, we can describe very nicely what these words are. And oh, I see what's been bothering me. I'm sorry. Yeah, I see what it is. I jumped the gun with the AIs. Yeah. I'm sorry. I should have done this first, and then these should be alphas. That's what you're saying. Yeah, I'm doing things and I skipped a step and I went back. Thank you. There we go. These are words in the alphas, which I'm going to explain. Okay, so let me. What is alpha I? Okay. Thanks very much. Now, the amalgamation that's going on here is on words in the alpha I. The word here is being associated to a word here. You're just being too polite to because in general you've got to be careful. I mean, these A1 for A2G may not generate H1. Okay, so what's the deal here? Now the AI plus is some word VI in the alpha 2Js, and if you want to read the contribution of alpha J in this, all you have to do is read off the linking coefficient, the linking nature. So this is simply a word. And why is that? Because if I push curve off, and I find that I link A1, that means I'm picking up a contribution of alpha 1 in the homology of Y. So reading linear numbers is the same thing as reading contributions to the homology in Y, given by this dual basis. Okay. And AI minus is given likewise. UI is another word. And that word is given by. And so now that I think that is correct, we can write down H1 of X prime as a module presentation TVI is I is 1 contingent. And I'm using round brackets just to tell you when you're dealing category or something. This is a module. So as a ZT Timbros module. You've been using it like that. All right. So you take this example here and just continue it. V is that's right. Is minus 1, 0, 1, minus 1. You can check that. And then U is the transpose. And in fact, you get more than just the Alexander polynomial. You're actually using this. You can actually write down what the homology is as a module. And so the first homology, if you wish to have it this way, is alpha 1, alpha 2. A T of, just read it off, minus alpha 1 equals this contribution, minus alpha 1 plus alpha 2. And then T of alpha 1 minus alpha 2, reading it off here, is equal to this word in the alphas, which is minus alpha 2. And now you've got your choice. You can solve for alpha 1 in terms of alpha 2. You can solve for alpha 2 in terms of alpha 1 if you wish. You can simplify this. And in fact, if you solve for alpha 2, then you just get alpha 1, and you just simply get t squared minus t plus 1 times alpha 1 is 0. And so the first homology is a cyclic module. And the Alexander polynomial is given to us. If you, I won't describe this for private time, but if you take this band here and you put a figure 8 knot into it, or I'm taking a figure 8 knot with a nice blackboard framing 0, or you take a trefoil and you put it in and you put enough corresponding twists here to make the ride of the band 0, you'll produce Alexander polynomial 1 that's this way. You can see what I'm using. So this is a nice way. This approach has big advantages over vertigo presentations and doing things
What
with
were
it.
you saying? Can you repeat?
Oh, yeah, sure. If you want to get an Alexander polynomial 1 knot, you can take this and say put a trefoil knot into it, and then depending on what the ride of that knot is, you can put some corresponding, some canceling half twists in the band. And you
I mean, if you put in a knot with 0 ride into the band, then you shouldn't change the Cypher matrix at all.
Precisely.
And so you don't get Alexander polynomial 1, you get this other polynomial.
You get the trefoil.
Let's see what we're going to get. Oh, excuse me. I'm gonna cancel out the ride. I'm gonna make the 0 linking number in this band use.
Oh,
Yeah,
okay. So
I'm
it'll
sorry.
look
Yeah,
like the
I
okay.
said it very stupid. I'm sorry. Let me do it. This doesn't take me to do this. Oh, it
You
always.
could use the overhead.
Yeah. Isn't always this way. There we go. Okay, I'm through now. Bring it down, and then take this one over, and just do what we did with the other one.
Oh, okay.
That's all. Yeah. Okay. And if you do this, actually, I think you get V is 0, 0, 1, and delta. So it's a nice quick way to see something. Yeah, I should have said this cancels out the run addition. So the linking of this with itself, when you push off A1 is 0. That's what we do. Okay? All right, so that's all. Let's say what Lynn did and what has to change. So now assume S is regular. What do I mean? Well, every Cypher surface has a spine. You can think of the spine as just given by the two curves alpha 1, alpha 2. This thing will contract onto the spine, onto these two curves, alpha 1, alpha 2.
You mean A1, A2?
A1, A2, sorry, yes. And so by regular, I mean the spine. It's standardly embedded.
So just so I understand this, the picture of the Alexander polynomial 1 knot that you drew is not regular.
I'm about to say that.
Okay.
That's exactly right.
Because he has a picture, he talks about regular Cypher surfaces in his paper, and then he has a picture
that was one reason why
it's not regular.
Actually, I was thinking that's why probably why I wanted to draw that.
Okay.
But you know, you just say it, put a knot in it, right?
Right.
Yeah. This is an example of a regular Cypher surface. You've got a bouquet of two circles. They look a little kinky, but you can undo them by asymptotic, no problem. This one is certainly not. Okay. So. Now the reason he wanted this is that y then, what you get by cutting open is a handle body, or equivalently, the fundamental group is free. Sometimes, so you would say that S is a free Cypher surface because it's cutting along it gives a handle body, but this is actually a stronger condition. And yeah.
Is there an easy example of this
something
difference?
that's regular but not free?
Yeah.
I'll put it up to the audience.
I think it's not important.
I know there are examples.
Okay.
I doubt it's very obvious. Lynn needed this because of the way he was looking at things, but actually it turns out that to get an invariant, we can see very easily that Lynns approach, fairly certain of this, that Lynns approach would work perfectly well for free Cypher surface. But if you're following his paper, because he wants to make sure that he can get from one of these Cypher surfaces to another by sufficient nice moves, he needs the secondary condition. So let's see. Regard. Now this is a A1 2J and alpha 2J as bases for pi 1 of S and pi 1 of Y. And to do this, we have to be careful with base points and base paths. We have to choose for the particular. And there's some obvious ways to do this. If you imagine the Cypher surface S with its positive direction, then we can imagine a little sandwich. This is now S, and this is the positive push-off on the Cypher surface, and this is the negative push-off. And we could pick this base point down here, just kind of drag it down here. And we could choose it right here, say. And now to get up to a base point on S plus, we could go straight up here. And to get down, we can go straight down. And so this would be a way of basing everything in naturally. Okay. So now we've got curves from along here, so at each one.
And which would be the base point of Y?
Which would be the base point of Y? That's a
The one in S plus.
yeah, the one. You got to make that choice, but I would use the one that has plus. If this is Y, it would be there. And to get to the other things, you have to travel along the meridian some number of ways. So generally, what you're going to see is some number of copies of the meridian conjugating to get you into other copies. Right. So now, so now if we push off AI plus, now this thing is still going to represent a word, and AI minus is going to represent a word. Okay. And we're going to consider the matrix Fox partial of VI with respect to alpha j. So we're really interested in this free group right here. Push off an AI, read it as a word in the free generators of the fundamental group of Y, which is generated by alpha 1 through alpha 2G. Focus on alpha 1 to alpha 2G. And consider the matrix of Fox partials. Now, this matrix has entries that are polynomials. If you augment this thing, if you send all the AI alpha i's equal, set them equal to 1, then the matrix you get is big. Because all you're doing is measuring linking, keeping history of where you've been. All that this matrix does is it as you travel around, as you go and link around. You can think as you link around one of these handles, you've got a monomial which is telling you your history, where you've been, and the Cypher linking matrix forgets all that history. I'll show you examples, but that's how to think of it. And likewise, that UI alpha j and u, and likewise this thing. Oops, ooh, sorry, what am I saying? Consider this, and of course this thing goes to you. Now, remember that we've got a representation every time we talk about twisted invariants. We've also got a group the knot, and the group you can think of as being a quotient of the free group on its generators. So we've been used to notation of F for the free group generated by, in this case, Vertinger generators. This would be the knot group with the relations. The relations. You can use it. You can use any generators and relations you want now. We've got a lattice version of this. Let's just think of it this way for a moment. We have epsilon augmentation, which takes you from pi to z. We call that as free group generated by t. And then we have a big, which sends us from the group ring of the free group to the matrix group. So this is we've got a representation. I haven't written that down. Gamma pi to GL n R. R is always assumed to be Invariant to FT. And now we get from it this thing called B from the group ring of free group to n by n matrices or lambda, where lambda is our TT inverse. And just think about it this way. Xi is going to go to the augmentation of Xi, the matrix that Xi goes to under our representation. And this augmentation for a Vertinger generator is just T. And this matrix that little xi goes to, we are denoting by capital Xi, just as a mnemonic to keep the notation down. And then you extend over the group. Here I'm being a little loose about whether Xi is in the free group or is in the group. Okay, it's not going to cause us too much trouble. But if we take an element alpha I is in the commutator subgroup. And this is going to go to, well, this is going to be 1. And we just denote this by counter. So now what we want to do, we really want to consider not these matrices, but these matrices evaluated. So define, finally, the twisted, we could call this the twisted Cypher matrix, so I don't think it's probably not a very good name for it. And this is a cumbersome notation. It's sometimes better to write this as feet up above. Just to indicate if you want to cut down on your parentheses. That's what might be good. And likewise that. Anyway, before I go on, let me mention this is as close as I can come to any reasonable definition of twisted linking numbers, and it's not much of a definition at all because it's just the Fox partial derivatives. It would be nice to have something that's maybe a little bit more geometric about linking numbers. And I only know of one paper by Calagoe that talks about this issue at all, about defining twisted linking numbers. And the paper is not as general as one might hope. Keep in mind that it would be nice to maybe explore this business a little bit more. But here's the claim. The claim is that the Wada invariant, which we've been denoting by W, and we know has determinant I minus T, x, where x is x0, or x is our meridian. You can choose any one you like. Choose x0. Is the determinant on the top of T times a, this is a block matrix where you've got little n blocks corresponding to.
Now capital.
Oh, sorry, 2G. Sorry, this should be This should be 2G. Right? Okay. This should be 2G blocks because it should correspond to the alphas.
And capital X, that's the same as capital X naught?
Yeah, capital X is the same as capital X naught. Thank you.
So you've got a couple of X's.
Do I have a couple of X's?
Well, it's not exterior, so.
Yeah. You can't. Okay. So this is U gamma minus gamma. This is almost like what we wrote down for the untwisted invariant. It's in fact, if the representation is trivial, this is delta of T inverse 1 minus T, which of course is equivalent to units, the delta T minus 1. And when we go to the twisted Alexander invariant, this difference between delta of T and delta of T inverse, while it's not important for nice representations, such as unitary representations, which is in fact proved by Chuck and Paul Kirk. It does not hold even for SLN representation, so be a little bit careful with this. So what's the reason for explaining that? And so the numerator of Wada is the polynomial that Susan and I have been calling D, capital D. And so we've shown that this capital D is Lynns polynomial. That's why we said it should be perhaps called Lynns polynomial recently. So the reason is that pi1 of the infinite cyclic cover is just copies of this free group, now amalgamated with UI equals. Now, the action of multiplication by translation by T corresponds to conjugation, but conjugation in this way, T inverse VI of T. And so I'm thinking of the UIs as living here. I'm also thinking of them over here. And I've got a letter T. Oh, by little x. Thank you. By little x. I've got x. Thanks very much. I've got this new letter, so-called stable letter, little x.
Which is little x naught.
Which is little x naught, right?
Is that the meridian?
That's the meridian. And it's got to be this way. I'm making this point to save some people a lot of trouble, because it will make a difference in the calculations and so on. I've got a handout that I'll give you in a few moments of a nice example where everything's worked out by Chasson. But if you go through and you do this bit of it, you find out that you absolutely have to have this or all hell breaks loose. Okay, so what's the deal then? That means pi, the fundamental group, is given by x alpha 1, alpha 2g. This is sometimes called an H and N, an extension of the free group, which is pi 1 of 1. You've got a new generator x, which is the meridian, of course. You've got your free group, and you've got these words that are being identified. Okay. And now all we have to do to see why this is the numerator of WADA is to compute the partial derivatives of the relations. And it's better to write this as x ui vi x inverse. And here's a useful trick. Useful trick is that if you've got two words, R and S, such as R's inverse is 1 under phi, then in fact, phi of the partial of this thing, with respect to any generator you want, is just the difference and I'll leave this as an exercise in Fox calculus. But what it means is that it's better to leave these alone, or simply write it as I think maybe it's best to write this as x ui equals vix for purposes of calculation. So you don't have inverses, and all you have to do is take the Fox partials of this and subtract the Fox partials of this. So this is handy. And it also tells you that when working with this calculus, relations are sometimes more convenient than really torus. Okay, so now the partial with respect to alpha j of x ui its inverse is of course the difference of x ui is the partial of oops, that shouldn't be vix. And when you do this, this is going to be you're going to pick up the x when you take the Fox derivative, and so let me write this as x ui the alpha j, and over here we're just going to get the vi.
Do we need phi of these?
Sorry?
Do we need fees?
So we're going to take phi now. We're going to apply capital phi to it. If you apply capital phi to it, this becomes t times the matrix big X. These are our entries, and so what we get. Let's see. That's dj. So let me write it this way. This whole thing will be so dj is tx times u. Oops. Look at that. this one. We're going to get this minus yeah. That's what we get. So the matrix that we get will be this, and this is what we've been calling the twisted Alexander matrix. Okay, so if you just go through this is what you get. And this is why you can take the T out. This is why you get this form over here. But warning, D gamma is not gamma transpose. I don't know if there's a nice way to see if there's some relationship here, and we've got nice representations. But okay, so with a few minutes that's left, oh, here's a. I knew I should not try to do this example. Let me give it to you because I really want to get to something else. And some observation comes out of this today. Talk a little bit about fiber instructions. And I knew if I did this, I'd regret it. So here's an example you can study. This is Chasson's example from his paper. Worked out a little bit further. Okay. And instead, let me use my last few minutes to say something about what this motivates, and state a result that's very pleasant and a little bit more general than corresponding results, I think, in the literature. So remember that K is fibered if the complement in its vibration over the circle, that's 1. In particular, what this means is that we've got the knot complement. There's many copies of the cyphered surface of minimal genus. And as you travel around, there's a gluing here. So this is S. And when you come back around, you glue to get X. And this is giving you the direction of the vibration. All these fibers are going to points. The points are preimages. Points are preimages of preimages of points under this submersion. But in particular, what it means, though, is that if you push off from this Cypher surface in either direction, this Cypher surface is this Y is a product, and so the push-off maps are actually isomorphisms on fundamental groups, because this fundamental group is this fundamental group, and this fundamental group here, and this side is this one, and so. And so these push-offs give isomorphisms, and one would expect that in the fibered situation, the polynomial here would have maximum possible degree and be monic. That is, the coefficients. In fact, the coefficients on either end you would expect would be units. And this is indeed true, and it's been proved by a number of people. So we've been calling this thing on top D. D gamma. Let's continue to do that. We expect that D gamma is monic on both ends. And degree, by degree of a Laurent polynomial, would just mean largest degree minus smallest degree. The degree is should be twice the genus, which is the genus of the knot now. It's the minimal genus. Minimal genus Cypher surfaces for fiber knots are unique on the isotope of the outer fiber. Times the size of each representation. Representation of numbers, capital N by capital N. And this is true, and it's been proved in a lot of different forms by Friedel, Ducey together, Cha, Tano, and Morifuji, Goda, Bajitov, Pachinov, and Kitayama. And it's been proven in greater generality than this. It's been proven for free manifolds that have non-empty toral boundary in some sense. Non-empty boundary has been proven in various ways in some sense for free manifolds that have non-empty toral boundary. And let me sketch the idea for something that's possibly more general than these. I haven't looked at every one of the papers, so what I'm saying might be quite boring. But here, theorem. Let pi be a finitely presented group epsilon, an epimorphism from pi to z such that the kernel of epsilon is a finitely generated free group. Let's say f a little n. Then for any gamma from pi to GL and R, where R is in the theory and UFD as usual. Number 1 degree of D is little n times big N. In this case, little 2g times n, and 2, leading and trailing coefficients. Up to gamma are units. So we can make, so the first one, 1. They're really, if you look at this, remember that x is invertible. X is invertible. And if you look over a sufficiently large extension field, you can certainly put x in upper triangular form. And down the diagonal are going to be the eigenvalues, right? Which will multiply to the determinant of x, which is union. So if you look at this, you can see that this expression is going to give you a leading coefficient of t to the 2n, the number of these, t to the, n, g. The real issue comes on the other end, on the constant coefficient, and whether or not that's non-zero or a unit. So the idea here is that just go ahead and mimic this argument. You choose x and pi, so this is a sketch of the proof, such that epsilon of x is 1. So just take an element in pi that goes to 1 under this epimorphism to z. And then we can always write pi as in so-called H&M extension. These are the generators of the kernel of epsilon. This is something that goes to 1 under the under epsilon. And you can write this as x. A1, x inverse, some phi A1, x inverse is phi A. Where phi is some automorphism of the free. And then you write down, again, we're computing the Watt invariant here. We've got a representation. So we write down and gamma, and the whole thing goes through just like we did before. Over there we get a t times x, where these are n by n. This is little n by little n. Oh, sorry, they're n blocks. And over here we get evaluating. So That's the situation we have. And as I said before, over a splitting field, this is upper triangular. So it follows that the determinant of m gamma is equal to t little n big N times the determinant of x raised to the n power. This is a unit.
So why is our U alpha not up here in this formula? For
Alpha.
For m, U alpha. Yeah, we
U
have m
alpha.
alpha.
So
And gamma, I mean, sorry.
So remember that Lynns, that the U in V in Lynn is used to get these relations. What's going on here is actually the push off in one direction followed by the inverse of the push off in the other direction.
The U alpha.
Yeah.
So it's like turning the thing in the right into
Yeah.
the U alpha.
So if you think about push off in one direction as an automorphism from the free group to this free group with respect to one basis, and this push off is another free group automorphism. This is actually the composition of one followed by the inverse. That's what's happening. It's been sort of pushed over to the other side. And so now. So what about the last term? What's the last term? The only observation really to be made is that this thing is a unit. And the reason it's a unit is because this matrix, J, called JB, has a right inverse in n by n matrices over ZF. And this is a theorem of Berman. I forgot the year of this theorem. It's a theorem of Berman, and she called the right inverse B. It's very amusing because what you're saying is that John Berman, is he at dinner? I don't think she meant to do that. And anyway, the point is that if you formally replace
JB is I, as the author speaking.
right, replace the AI by the matrix AI, which is what little AI goes to under the representation. And of course, if you see one and you replace it by I, this is a very simple observation. Then the formal multiplication that's going on here, remember that this is non-abelian multiplication in group rank. If you see a little AI butting up against a little aj, and when we replace them by matrices, you see the capital AI butting up against the capital AJ. They cancel, and the same thing happens. So because they cancel in the free group, because you're going to get an identity matrix in the free group, you're going to get an identity matrix with your values. And so that tells you this has to be So this is actually a pretty good abstraction for fiber, and there are a number of questions that are still open about it. One of the natural questions is, to what degree can you go the other way? And Friedel and Medusi have a really nice result about going the other direction. I'm trying to say it now, but there's a question remaining open. What kind of representations do you need? And frankly, there's also the question: do you even need this degree condition? So I'll ask this question: if D gamma is monic on both ends for all finite image reps, or permutation reps. Just take permutations. It's the same thing with the conjugation. This is for a knot. Is K a fiber? And the answer to that is no. And if you want, you can add monic with the expected degree. But even this much.
So do y'all have like Have people looked at this question enough to look at like small bad guys, small bad examples, and rule them out? Rule that they actually, like, so some knot that's hard to tell by looking at, say it's Alexander polynomial, whether it's fibered or not. Say it's Alexander polynomial,
Right.
pretend that it's fibered,
Yeah.
but it's not.
Yeah.
And
Yes.
then they look at this for that small example, and this is what actually comes up.
Now this is, I think this question is made it into Stefan's survey paper or something. Right. So anyway, I'll stop here. Thank you very much. Tomorrow we'll do a different topic.
Well, thanks. Any questions?
All right, this may be a technical question. What goes wrong in Lynns' paper if he doesn't assume regular Cypher surfaces?
Well, it's argument. Is the result still correct?
He needs to have
Yeah.
moves.
Yes.
He needs to have moves on
Regular.
that surface. And he gets them from just being handle additions.
Right.
And that gives a very particular form for what this, the new matrix is with the new cycles.
But of course, it would work perfectly well if you used a free Cypher surface. We know that from Lynns' arguments. Let me toss out an idea, though. I was going to say something about this if I had time. There's a very famous, not terribly hard to prove result that says every knot in a homology 3-sphere, where you can compute Alexander polynomials, linking matrices, everything's fine. What you mean is homology. Every knot in a homology sphere has an Alexander polynomial that's realized by some knot in S3. And the basic idea for this is you span the knot, and you, by a Cypher surface, you know that you can convert the homology sphere back to S3 by plus or minus surgeries on some link. So you put a Cypher surface on that link, you put a Cypher surface on the knot, and now you move the knot without changing its type. You move it off the Cypher surface, and essentially these two Cypher surfaces are just trying to create a boundary. Why is this? Well, because every Cypher surface is essentially one-dimensional. You can push things off without changing the type within the homology 3-sphere. And now the linking form for this knot doesn't see the Cypher surface for the link on which you're going to do plus or minus 1 surgeries. And so doing them won't change any of the form. You get a knot, some knot in S3, you're done. It'll have the same Alexander polynomial. Is this true for homology 3 spheres with twisted invariants? There are a lot of hurdles here, but stated this way, given a representation of a homology 3 sphere, of a knot in a homology 3 sphere, is there some knot in S3 in representation of its group, so that the twisted invariant will be the same? One of the first problems is just pulling back the representation. Because, anyway, that's the first problem, and then the other problem as well. If you look at Lynns' approach, if you want to look at the twisted V and the twisted U, they're possibly going to get tangled up inside the link on which you can do surgeries. Just because they, it's not clear, but I'm guessing it's yes. If there's a simple group theoretic reason why the representations can't correspond to something, that would be interesting too. But this is another thing, it's the kind of thing that gets motivated by Lynns' approach that you don't see from the combinatorial approach in Wada, and I don't think you can see in the homological approach that we'll talk about tomorrow.
Thanks again.